when we crank to create the voltage to move the electrons through these wires, assuming that this is a bulb with a thin wire and this is a bulb with a thicker wire in this case, relatively thin, relatively thick, maybe not all that much difference in thickness, but this one's certainly thicker than this. We're going to have the same number of electrons flowing past a point in this wire as past a point in this wire, and of course past any point in the connecting wire. This wire, on the, however, being thin, will resist the flow of electrons more. So we have this 0.2 coulombs per second, and in order to crank the electrons through here, if we were just cranking 0.2 coulombs through this wire, we would have to crank harder than if we were cranking 0.2 coulombs through this wire. That is, okay, we take the leads from the generator, put them here and here, and we just crank the electrons through this wire. Then we do the same for this wire, leads here and here, just crank the electrons through this wire. We're going to have to provide more voltage to get 0.2 of a coulomb through this wire than through this wire, because this wire is thin and resists the flow of the electrons more effectively than this. So we're going to need to pump harder. We're going to need to crank faster here. Okay, so the faster cranking here, slower cranking here because of the greater resistance to the flow of electrons. Now this is assuming that in both cases we achieve 0.2 coulombs per second of current through the wires, which is the case. Now if we hook these wires together, okay, we no longer set the generator across this one or across this one, but we set it from here to here. The same current flow has to take place through both wires. You're going to have more voltage across the thinner wire than across the thicker in order to get the 0.2 coulombs per second. Okay, more voltage to get this number of electrons through the thin wire than through the thick. Now, we define resistance by thinking about this situation, okay? The resistance we're going to define as the ratio of voltage over current, okay? And that makes sense. If we need a higher voltage for a given current, that means that the wire is resisting the flow of current. Okay, similarly, if we get a high current for a given voltage, that means that the resistance would be low. So if the numerator is high here, that means a lot of voltage for the current, which means that we have a high resistance, because we need a lot of voltage to make the current happen. Whereas if the denominator is large current for a given voltage, then of course a large denominator is going to make R less. Less resistance gives you a greater current for a given voltage. So you can think about this proportionality, which is all it is. And resistance is just a proportionality between voltage and current. And you can think about that in terms of real situations with thin wires, thick wires, greater resistances, lesser resistances. If we have a current through here for a given voltage across here, then the resistance is voltage over current. And these are things that we can measure and that you do measure in some of the experiments. And we've got this. A high resistance means we need more voltage for a given current, or alternatively less current for a given voltage. That would correspond to a thinner wire and to easier cranking. Okay, so high resistance, less current for given voltage, easier cranking. A low resistance would be more current for given voltage, harder cranking. Okay, in a minute we'll look at how resistance is combined in a circuit. And we'll see some of this symbolism, some of these conventions for drawing circuits.